Next talk is by Salvador Borrós from Universitat Autònoma de Barcelona. And the talk is, the title is Computing Rotation Numbers in the Circle with a New Algorithm. So, Salvador, endavant.
Thank you, David, and I would like to thank the organizers for allowing me to talk in this workshop where so many distinguished guests are here and presented, which doesn't make me nervous at all. In any case, as the title suggests, we are going to present an algorithm to compute rotation numbers in the circle. I know this is failing me. Okay. Mainly, this presentation is a simplification of this paper here that we have published with Luis Alzada in arXiv, and we are pending for a journal, which probably will happen soonish. We don't really know. And moreover, most of the results I will go on citing can be found in the so-called the Bible of Combinatorial Dynamics and Entropy in Dimension 1, with two of the authors present in the public. Okay, first, let us introduce some basic concepts for the people who are not so familiar with the topic. If we have for us, S1 will be R over Z. So we're considering that the circle has length 1. And recall that for a given, for the circle, there's the universal cover by R, which simply is this map I to pi with the x on it. And then if we have a map from S1 to S1, F, and we have here the universal cover in both branches here, there exists a map F such that this diagram commutes, and we say that this map is a lifting of F. Note that, however, this lifting it's not unique by any means. However, we have a nice property that says that if we have two coverings, then they are just one translation by an integer, one from the other. So they are not the same, but mod 1, or essentially they are the same. And we say that F is of degree 1. Both lower and upper F's, it's sometimes it's confusing. If F of 1 minus F of 0, it's equals to 1. I think it's easier to understand with an example. Here we have a circle map. Note that it's periodic, and the upper bar it's identified with the lower bar. If we get a lifting, what we get is sort of the same shape. This piece on the bottom, we just put it on top and then sort of repeat it, like increasing. Just here we would have a copy of the same map, sort of all over and going down. And we say that it's of degree 1 because the difference between this and this is exactly 1. So now we have maps in the circle. What about the rotation number? So if we have a lifting of a map of degree 1, we will define the rotation number of F on a single point. That's important. The rotation number a priori depends only on the point. Or it depends not only, depends on the point, also on the map, as this lim sub here of F on this lim sub here. Notice though that this definition it's not as general as precise as it should be. This actually usually is that it's like the upper rotation number, and there's a similar definition with the lim inf. However, since in this case we will be studying only non-decreasing maps, we are not that concerned on these small technicalities because our results will still work. So since this rotation number is dependent on x, we may ask ourselves, okay, what is the set of rotation numbers that are like our points in R may have? And this is called the rotation set of F, and Ito in the 80s, I think, proved that this set is actually an interval, a closed interval. So we would like to be able to compute the rotation interval for general maps that can also be used for non-invertible and non-differentiable maps. And the question why? Well, first, like we're mathematicians, we like problems, and okay, there exists plenty of algorithms to compute rotation numbers on intervals for differentiable maps, but the general case is a bit forgotten. And also, at least what I'm more familiar with, there is some theoretical importance to it as well. In combinatorial dynamics, the Misirovich theorem tells us that the set of periods of maps of the degree 1 depends, among other things, on what the rotation interval is. And also, lower bounds of the entropy of circle maps of degree 1 as well require sort of knowledge of the rotation interval. So it's not something that we are bored and would like to know, but it also has some theoretical importance as well. So let's start by paving the road. It's not trivial, but we will find some maps that will allow us to simplify the problem and compute it in a nice way. The first step of this path would be to notice that non-decreasing maps have a defined rotation number as a limit, not as a lim sub as before, and the rotation number for all points in R is the same. So we can start define for non-decreasing maps, we can talk of a rotation number for the map, not for the map and in a point. Remember that back in the previous slides, we always wrote rho f of x. Now it's just rho of f for non-decreasing maps. And this may lead to a first naive algorithm to compute rotation numbers, which would be okay. Since we have a limit here, if we can see what the convergence is, then we have an algorithm. We just go on iterating the function and computing this number. And at the end, eventually, we will get close to our rotation number. We have to check how quick we get there. And we have this lemma here, which it's a bit messy written, lots of inequalities and definitions which are not super intuitive, but it's very easy to understand with a picture. This LF of n defined here is just, okay, x plus LF of n, it's the lowest diagonal, the highest diagonal that is still below f of n of x. So this is pretty straightforward. If we have this lower diagonal, then we know that our function, since it's non-decreasing and of degree 1, so this distance is at most, well, it's exactly, not at most, it's exactly 1. And we know it cannot go very high up and then go back down because it's non-decreasing. Our function will be between this diagonal and the next. And mainly 3 things can happen. Either this function touches the diagonal on 2 points, it's in between, or touches the upper diagonal. In any case, since the iteration of non-decreasing functions preserve inequalities, we can see that the rotation number, like this approximation of the rotation number just by iterating the function, gives us an error of at most 1 over n. So now we have a control over the error. Now we have a sort of a naive error algorithm, which is not very nice. It only gets us approximations. It's not, and it's 1 over n. Maybe we can expect something more. However, this is to come yet. However, let us first, though, talk a bit about the upper and lower functions, because these are very interesting functions that we may use to compute the rotation interval, because they are non-decreasing. They are built by this formula here. However, I think the intuitive idea is, okay, the upper function is built if you start pouring water from here, and then the water would fill all the nooks, crannies, valleys, and you would get a non-decreasing function sort of made by the water. This we will call the upper function, and then the lower would be done by being in Australia and pouring the water, sort of the other way around. And sometimes they are called also water functions, but they are the same. And here there's this nice theorem that relates the rotation interval of a function with the rotation number of two non-decreasing functions, the lower and the upper function. So we have that the rotation interval, it's actually given by the rotation numbers of this lower and upper function. Hence, we could give the first naive algorithm to compute the rotation number, interval of a map, that would be compute the upper and lower water functions, which this can be done sometimes numerically, sometimes analytically, it depends on the function. And then just compute the rotation number of FU and FL. We have an algorithm that we have called naive algorithm that allows to do this. However, we want more. We want to be more efficient. We want to be more precise. What we have is not enough. And to do this, we will have to deal with periodic points, which it's what you would expect in this sort of workshops about topological dynamics. However, note as a side note that if we have a non-invertible function, then our water functions or upper and lower functions will always have constant sections, either because the function itself has a constant section, or whenever we have a valley or a mountain or whatever you want to call this, the water function will go above it, filling it in a constant section. So these sort of maps for our case tend to have lots of constant sections, and that's exactly what we will exploit later on. Then, as I said, we will have to deal with periodic points. However, okay, on the circle, a periodic point, it's something like very easy to see. Like you go on and then you fall again where you started. On liftings, you have to be a bit more careful, because since a lifting sort of goes on increasing, you have to define periodicity module 1. That means that a point is n-periodic mod 1 if there exists some integer such that f of n of x is equal to x plus this integer. So f of n of x is equal to x mod 1. And this n is the smallest one for which this thing happens. And in these cases, when we have a periodic and periodic point, then we can compute exactly the rotation number of this point, which it's simply this k here divided by the period of the point n. So they have this nice property that you can exactly determine which is the periodic point. For example, we have this example here. You have that point 2 goes to 0.3, 0.3 goes to 0.7, and 0.7 goes to 1.2, which is 1.2, it's 0.2 mod 1. Therefore, we can say that the rotation number of 0.2 is exactly 1/3, because the difference between 1.2 and 0.2 it's 1, and the period is 3. However, this is a non-decreasing map, so we can safely assure that the rotation number of the whole map is 1/3. That's the nice thing about non-decreasing maps. Finally, we have all the pieces in place to present the main proposition of the paper, that says that if we have a constant section x such that there exists some n, such that the nth iterate of the constant section intersects the constant section modulus 1 again, and n is minimal, then we can assure the existence of an n-periodic point, and with this n-periodic point, we can compute the rotation number of our map. Sorry, I didn't say it was non-decreasing. Yes, that's very important. Going back to the example as before, if, for example, we start iterating 0, since it's in a constant section together with 0.2, it doesn't matter. The image of 0 still is 0.3, right? So eventually, for example, in this case, we will fall again within the constant section plus 1. And if you see, it's 1, 2, 3 iterates, and the difference here is 1 again. So we can assure now that the rotation number is 1/3. What we gain with this proposition is that, okay, finding periodic points may be very hard. However, if we have a constant section, the nice thing about it is that you have a set that doesn't have measure 0, and just by iterating all of it, it's easier to catch a periodic point when you start iterating it, right? So it's sort of you have a big landing strip for a periodic point to fall into the constant section. However, note that you require that a periodic point is inside the constant section. And this we will talk when we talk about the limitations of this algorithm. However, using the naive algorithm and this proposition, we can piece together a dual algorithm, so to say. This algorithm will try to find the periodic the rotation number in exact manner using our proposition, and if it fails, it will just reduce to the naive algorithm. So first, using the error estimates of the naive algorithm, we set a maximum error, and then we can compute the number of iterates that we would have to do to get this error. Then we reparameterize the lifting so that the constant section that we have chosen to iterate it has the form 0 beta. And of course, beta is less than 1. Why? Because once we start checking whether or not the iterate is in the constant section, if it's of this form, we only have to check one inequality, not 2. Then we initialize it at 0, and we initialize m equals to 0. And then so we go on iterating and making the iterations modulus 1 and just saving the m to compute the rotation number in case it's necessary. And then we check at each iterate whether or not x is less or equal to beta. In this case, we apply the proposition and we get an exact rotation number. Of course, exact in the sense of that theoretically should be exact. When we're talking about computation, there are truncation errors that may propagate during the iteration. So we have to be a bit more careful. However, if this never happens and we reach the maximum number of iterates, we can default to the naive algorithm and then get an estimation of the rotation number again with an error bound of 1/n. Note this, however, that the algorithm that can be found in the paper, it's more nuanced than this one. This is a simplification. The one in the paper takes into account possible rounding errors, truncation errors, and so on. This algorithm, however, has some limitations. First of all, and it goes without saying, it won't compute irrational rotation numbers because we rely on periodic points to compute rational rotation numbers. However, we may also have, for example, in this case, we have here a 3-cycle that it's outside the constant section. And one can easily check that this constant section actually doesn't have any 3 periodic point or any periodic point at all. So even though we know that the rotation number of this map is 1/3, from our algorithm, we would not get the exact 1/3 rotation number in a nice manner. However, we must say that all the examples that we have found with rational rotation number that have not used our proposition have been made ad hoc to have this sort of behavior. All the natural examples that we have tried always have had some sort of periodic point in the constant section. So what is an algorithm if you don't test it? And we have taken this family of one parametric map and sort of computed the devil's staircase. Recall that the devil's staircase is what you get by plotting the rotation number in function of the parameter of this one parametric family. And well, we have chosen n to be 10 to the 6, and we have done 10 to the minus, like the step has been 10 to the minus 5, so 10 to the 5 points. And you can see that the time taken by our algorithm, it's 5 orders of magnitude less than using just the naive algorithm. In the paper, you will find that we have also tried another algorithm by Simon and some other authors, and still our algorithm outperforms by at least 2 orders of magnitude this other algorithm. Also, of course, like these 2 pictures side by side don't tell you much. However, the error is within acceptable bounds. I know that there is some 2 to 10 to the minus 6 here, but of course the computers also have truncation errors and so on. So one should expect that there may be some room for an extra error. And finally, we have used this family of non-differentiable biparametric family of non-differential maps to plot the Arnold tongues. This is just getting the triangle sine wave that goes like this, and sort of construct a similar, like a standard map, but instead of using the sine wave, using the triangle sine wave. And we have been able, in fact, to compute the Arnold tongues. We must say that in our paper, we also tried to compute the Arnold tongues with the same level of precision with all the other algorithms tested. And we had to stop it because we were more than 100 hours plus of computation, and this barely took more than 20 minutes. So we thought that, okay, the comparison, it's well enough. We had to put the cutoff somewhere, and it was not that important for us to compute exact nice Arnold tongues with algorithms that we hadn't developed. However, using both of the algorithms with cursor parameters also gave the same figures, so they were proper. So the algorithm works as expected, so to say. And that would be all, and thank you very much for your attention.
Thank you, Salvador. Nice algorithm. So question.